Welcome to our next lecture in this series on condensed matter theory. In this lecture I want to talk about the self-energy introduced due to disorder for electrons propagating in an otherwise perfectly periodic lattice. What we have seen in the Drude or Sommerfeld model is that in order to describe the conductivity of electrons, we assumed that our electrons move with a certain momentum. And in this case, there was no periodic potential, so this was real momentum and not crystal momentum. And then at some moment in time, there was a scattering event. And after the scattering event, the electron would move with a different momentum, K prime. And the probability to scatter, P to scatter, was given such that in a time interval T to T plus delta T, the probability is equal to delta T divided by tau. So that tau is an average time between two scattering events. And with this we were able to derive Ohm's law in one of the first lectures, as the conductivity is such that the current is the conductivity times an external electrical field, and the conductivity is given by the electron density times the electron charge squared times this tau in our scattering divided by the mass of the electrons. Then we introduced the periodic potential because of the atoms on a lattice, and where Drude and Sommerfeld originally assumed that the scattering would be of those periodic organized nuclei. We then introduced a crystal momentum that was replacing the real momentum. And we showed that the crystal momentum is conserved because you have translational symmetry, which means there are no scattering events. And we still had to introduce, even when we talk about Bloch waves, a scattering time tau in order to get a finite conductivity. And the only thing that this periodic potential does is changing the energy momentum dispersion relations, which then introduces an effective mass. Now in the later lectures we have been talking about Green's functions. And Green's functions tell you how an electron propagates from a state with one quantum number to a state with another quantum number. And as we take momentum as our quantum numbers, then we can have a look at the Green's function where you say, I propagate from momentum k to momentum k. And when this momentum is conserved, then I know that this has to be a delta function when k prime and k are equal to each other. You will always, when you create a particle with a certain momentum, you will be able to annihilate that particle with the same momentum. Now, of course, you can pick up a phase, so the Green's function is not equal to the delta function, but only the norm of that Green's function. And then, of course, when you try to annihilate the particle before you created it, you should not be able to do that. So this is only defined to be non-zero for positive time. Now if we look at the Drude or Sommerfeld model, then we can say, well, if I create an electron with crystal momentum k prime, and I want to see if that has the momentum k sometime later, well then for sure this is only non-zero if you try to annihilate it after you created it. But as we have these scattering events, and we know that there is a probability to scatter such that you go from one wave vector to the other, this probability is no longer conserved, and the expectation value to be able to annihilate an electron with wave vector k after you've created it with wave vector k decays with e to the minus t over tau. So what we want to investigate in this lecture is how we will be able to go from a Green's function that is conserving the crystal momentum to a Green's function where the crystal momentum decays, and ideally we should obtain a form that decays as e to the minus t over tau. Now we have been working with Green's functions in the frequency domain as energy is conserved in our systems, and this is often the easier way to handle your Green's functions. So let's translate these to frequency domain Green's functions, and we'll have a look at the Green's functions for Bloch waves. And there we can say that our Green's function, where we create and annihilate a particle with crystal momentum k with energy omega, is the limit of eta to 0, and we put our poles below the real axis of 1 over omega plus I nu minus, or I theta, epsilon k, where epsilon k is the energy momentum dispersion, or describes the energy momentum dispersion of our electrons. If we now Fourier transform this Green's function, then of course we know what the norm should be, but the full Green's function is again the limit eta to 0, e to the minus I, epsilon kt, e to the minus eta t. So if we now want to modify this Green's function such that we find a decay of a particle that you create at k into other states, then we see here that eta no longer should go to 0 but should become a finite number. So if we set tau equal to 1 over eta, we need infinite eta, and then we will be able to get the scattering time that we have in the Drude or Sommerfeld model, and with that a finite conductivity. Now the reason that crystal momentum is conserved is because we have translational symmetry. Not a continuous translational symmetry anymore, because then momentum would be conserved, but a discrete translational symmetry, which makes then our crystal momentum conserved. So in order to get a finite eta instead of going to 0, so in order to no longer conserve crystal momentum, we need to make a model that has no translational symmetry. And that is exactly what we do when we include disorder into our system. Now, in order to show you how this works and how disorder gives you a finite theta or a finite tau, eta, a finite tau, I will have a look at an example. And we take an example of a one-dimensional chain with a basis of a single s orbital. And we take nearest neighbor tight binding. Nearest neighbor tight binding. And as said before, these are not really necessary conditions. The only reason to do so is to make the math just less involved. So our hopping is going to be SS sigma, and the on-site energy epsilon s, such that the Hamiltonian without any impurities is a sum. J is minus infinite to infinite. The on-site energy, where we create and annihilate an electron on site J, plus our hopping term, where we hop from site J to J plus 1, or from site J plus 1 to J. Then we can have an impurity on site J, And for that, we'll take the Hamiltonian H1 acting on side J. In the end, we want to have a random distribution of impurities. And for that, we say, well, we have a different on-site potential. And of course, I want to add H1 to H0, so I just subtract the on-site potential that we had in the continuous periodic chain without impurities, times the creation and annihilation operator on side J. Now, in order to make a random distribution of these impurities, we'll define a distribution function. dj, and this is going to be 1 or 0, and it is 1 when there is an impurity on side J, and 0 when there is no impurity on side J. And we furthermore take P, the chance to have an impurity. So for each lattice side J, there is a chance P that dj is 1 or that dj is 0. With that, we can define our full Hamiltonian of the impurities, given as a sum over all sides times the distribution function times the Hamiltonian of having an impurity on side J. And the Hamiltonian of our lattice is the bare Hamiltonian without impurities, plus the Hamiltonian that tells you how an impurity brings you from the full Hamiltonian without impurities to the Hamiltonian with impurities. So minus the on-site energy of the host plus the on-site energy of the impurity. And of course, instead of doing this with impurities, you could also do this with hopping to the neighbors. There's not much changing in the way you do the method. At some point, the math will become more involved. And what we want to calculate is tau, the time that you have that an electron, when created with momentum k, stays in that state with momentum k. And in order to do that, we will calculate the Green's function in the time domain. And in order to do that, we will start with calculating the Green's function in the frequency domain, such that we then can Fourier transform it to the time domain. And in order to do this, we will first translate our Hamiltonian that we wrote down in real space to an Hamiltonian in k-space. So we want to Fourier transform the Hamiltonian. And when we take the steps in this direction, we should then be able to calculate tau that we had in the Drude or Sommerfeld model. So in order to calculate the Fourier transform of H, we can use that creation at site J is given as a sum over all crystal momenta, and then the normalization 1 over V, which for a discrete lattice can also be 1 over n, where you count the number of atoms, or V in units of the unit cell, e to the minus I k dot the position of your atom times the creation in momentum space. Well, if we add this into our Hamiltonian as well as its Hermitian conjugate, you will find that the Hamiltonian without impurities is nicely diagonal in crystal momentum, and we have an energy momentum dispersion of the on-site energy epsilon s plus 2 ss sigma cosine k dot a, where a is the distance between two atoms. A dagger K. AK. Now we can also try to Fourier transform our H1. And let's first Fourier transform the Hamiltonian for a single impurity. And if we do that, we have here something that is local in real space. So this should become something that couples all states with different momentum to each other. We have these epsilon s prime minus epsilon s. And then two Fourier transforms. So 1 over v squared times 1 over v squared becomes to 1 over v. A sum over k and k prime for the Fourier transform of the creation and the annihilation operator. E to the I, k prime minus k dot rj, because we evaluate them at the same position. A dagger k, a k prime. And from this you can already see that when rj is 0 and you can pick in principle still here any j value, that this is just going to be 1, and that you have an equal coupling between all crystal momenta vectors. And when you're not at the origin, you only have a phase, but the norm of the coupling is independent of the distance with which of the distance in k-space with which you scatter. So a Fourier transform definitely does not diagonalize this Hamiltonian. Momentum is no longer conserved. We will need this Hamiltonian in k-space, and for that we will gonna introduce H1 with an impurity on side j, scattering from k to k prime, where the Hamiltonian scattering from k to k prime is given as epsilon s prime minus epsilon s 1 over v e to the I, k prime minus k dot rj, a dagger k, a k prime. And then of course we do not have an impurity on a single side, we have a random distribution of our impurities. So if we sum over all sides, where we have a distribution function, and then our Hamiltonian j, k, k prime. So that is the Hamiltonian that we have to add to our H0 that describes the random distribution of impurities. Now, how can we deal with such a random distribution of impurities? And the good thing is we're not looking at some local properties where you go from a specific position in a specifically chosen random distribution from one side to another side. That would be totally dependent on how locally your distributions of impurities is organized, and this is different between experiment to experiment. So if you have such a system with local disorder, then you do a local probe, you really measure how you move from one side to the other, you should find that you get a distribution of measurements because your Hamiltonian has a distribution of how these impurities are really organized. If you look in momentum space, you're averaging by a Fourier transform over all these different possible random distributions. And what I want to show you is that for large systems, we find that the Green's function in k-space is equal to the average over all possible distributions of random orientations of the impurities. So this is the average over all distributions Gj. And of course you have a chance of P to have an impurity or not on each side. So that of course you have to fulfill. But given this chance of having an impurity or not an impurity, you can generate all distributions that then have a certain probability of appearing. You then average over all possible distributions with the probability that you have them. And then your Green's function will actually be the same for a specific realization of your distribution to the average over all possible distributions. And of course that is only true for very large systems. If you only have one atom, then it's either the atom or the impurity, and with a probability P you will find one or the other, and of course the Green's functions of those two will be different. But if your system is really, really large, then this is going to be true. And let's give you a proof of this. If we have M clusters of size n, and n is really large, so we have here a cluster and then another cluster, so a finite sized lattice in which we have our atoms, and we have many atoms, and n is large. Then our total length of the finite sized system is n times m. Well, when n is really large, then for such a single cluster you can basically neglect the surfaces compared to the volume. So the properties of this system are determined by the volume properties and not by the surface properties. If we now look at k vectors that are represented in the smaller cluster. So at gamma you have plus, 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 and that is okay, and then you can have plus, minus, plus, or plus, minus, plus, minus, plus, but the phase has to repeat an integer time within the smaller cluster. For those you will find that the Green's function of the larger system at wave factor k and k prime is just given as 1 over m times the sum over all clusters of the smaller size. Here at gamma you just sum each atom, creating and annihilating with the same phase, and at any other k vector you add a specific phase, but the phase will always be such that you start here again with plus 1, such that the Green's function of the full system is just the sum of the Green's functions of the smaller systems. Well, if we now have m large, so we first of all need n to be large, such that we can have surface effects, but when m is large, then the sum over a set of randomly chosen clusters fulfilling the probability that you have to find that cluster will become equal to the sum over all possible clusters multiplied with the probability that you find that cluster. And with that we find that the full Green's function becomes the same as the Green's function of the average over all possible clusters. What this basically tells you is that when you have a randomly distributed system and you now look at global properties such that you average over many randomly distributed realizations, then basically all possible different realizations of that random cluster will give you the same expectation values, which very much agrees with our observations in daily life. When we look at real materials, then we talk about the properties of gold or the properties of copper. And at the same time, we very well know that they always have some impurities in there. But still we can talk about the properties of these materials, because these impurities or the specific realization on how these impurities sit in that material are no longer important because you average over so many different realizations within that solid. So we're after the average over all possible random distributions of impurities in an otherwise periodic Hamiltonian. And of course we can easily solve the Green's function for the periodic system, and we can then treat the impurities as a perturbation to that system, whereby we have seen that just using perturbation theory for such impurities is not a good idea, because bound states can emerge, and at that point normal perturbation theory would diverge. But when we use the Dyson equations, we are able to sum up to infinite order and get away with these divergences in an otherwise divergent perturbation expansion. So we're going to use Dyson's equations. And what we know is that our Green's function, where I can travel from crystal momentum 2 to crystal momentum 1 with a certain frequency, is given by the propagation in our bare system, so the system without impurities, plus, and then we have to sum over intermediate crystal momenta, where we travel with the bare Green's function without impurities from crystal momentum 3 to crystal momentum 1. We scatter from an impurity or from the randomly distributed ensemble of impurities from crystal momentum 4 to crystal momentum 3, and we propagate with the full Green's function from crystal momentum 2 to crystal momentum 4. So we propagate with some wave vector in our full system, then we end up with a different wave vector because we should propagate in a system that is no longer periodic. Then you have a scattering event, and then we propagate in the system without impurities. And we can already see that we will be able to make a simplification here, because in the system without impurities, crystal momentum is conserved. So K3 has to be equal to K1. And actually we fully know what the bare Green's function is, which is delta K prime 1 over omega minus epsilon K, and let's put a 0 in there for the bare electron momentum dispersion, plus a small imaginary offset. In order to continue, we can of course now put in the full Green's function back in the Dyson equation, such to get a series expansion, and then our full propagator, where we go from crystal momentum 2 to crystal momentum 1 at energy omega, is given by the bare Green's function plus the Green's function, where we go with the bare Green's function from K1, and as this is the Green's function of the full periodic system, we know that crystal momentum is conserved, so we stay at crystal momentum 1. But then of course we can have the interaction with the impurities, where we scatter from crystal momentum 2 to crystal momentum 1, and we now put in the Dyson equation again, such that this is not the full propagator but the bare propagator, where you go from crystal momentum 2 to crystal momentum 2. And of course, when you put in the Green's of the Dyson equation back into the Dyson equation, you also get the cases where you have 3 interactions or 2 interactions. And for 2 interactions, we have to sum over one additional crystal momentum, because we can propagate for some time with crystal momentum K1. And these are all vectors. Then scatter to K3, then we have the propagation with K3, and we scatter of all the impurities to crystal momentum K2, and we propagate with crystal momentum K2. And of course we can repeat it indefinitely with 1 interaction, 2 interactions, 3, 4, 5, etc. Now we're not interested in the Green's function for a specific realization of random distributions, but we can calculate the Green's function for the average over all possible realizations, because if our system is large enough, they become equivalent. So we can make here an average over all possible realizations of the crystal momentum. And of course here is still missing that this only happens when the two crystal momenta are equivalent. Now the average of a sum is the sum of the average. So we can here take the average of each case individually, where you have no interaction with the impurities, 1 interaction with the impurities, 2 interactions with the impurities, etc., etc. And we should not stop this calculation at some point, because this well might be a divergent series, but we should be able to resum this up to infinite order and then get a valuable answer, which has to be the same, because we can always do analytical continuation, and all our functions are analytical with just a set of isolated poles. So in order to do this, let's first discuss these 3 cases separately, so that we see all the difficulties that we encounter and all the peculiarities that we have to take into account. And then devise a graphical method to write down these equations, so that we easily can see how we can bring this up to infinite order. And we'll then just discuss 3 cases: 0 interactions, 1 interaction, or 2 interactions. And once we have that, we should be able to generalize this to infinite interactions and then sum them all up. So case 1, 0 interactions. This is just the ensemble average of the bare Green's function, where we have no impurities, and the ensemble average over a system without impurities over all possible realization of the impurities is nothing more than the bare Green's function. So in this case, the averaging over all impurities becomes extremely trivial. The second case, where we have 1 scattering of all possible impurities in our system. And we have a propagation with crystal momentum K1, a scattering between K1 and K2, and a propagator with crystal momentum K2. Now G0 is the Green's function of the system without impurities, so that doesn't depend on the impurity distribution that we have. So we can take that out of the averaging over all possible random realizations of the impurities. And we see that we are taking the average here of the Hamiltonian, or better said, the Hamiltonian matrix element between states K1 and K2. Now, if you want to calculate this expectation value, then we can have a look at the definition of that Green's function. Which should be here. There we have it, which is a sum over all sides. So it's the average of the sum over all sides times the distribution function, which is 1 or 0, depending if you have an impurity or not, on side J with probability P, and then the Hamiltonian for a single impurity, which is a sum over all k vectors which is the impurity potential 1 over V. It's not a sum over all k vectors because I look at a specific case going from k2, kk1, e to the I k2 minus k1 dot rj. And here, of course, you have the creation and annihilation between k and k prime, but here I look at the expectation value between the states k2 and k1, such that k and k prime become k2 and k1. And we have to average this over all possible realizations of the impurities. So we can first of all take that impurity potential outside, epsilon s prime minus epsilon s. And now we can turn around the average and the sum. The sum over an average is the average over a sum. dj 1 over v e to the I k2 minus k1 dot rj. And here the only thing that depends on the random distribution of your impurities is dj, and the average over dj just gives you the probability to have that impurity. It's a probability p1 and probability 1 minus p0. So this is going to be equal to the average over dj is the probability p, epsilon s prime minus epsilon s, and then the sum over all lattice sides, 1 over v e to the I k2 minus k1 dot the position that we have. And what we see here is just a sum over all rj of an oscillating function, and that becomes a delta function between k2 and k1. So if k2 is equal to k1, then this is just the volume, so this is equal to 1. If k2 is different from k1, this is an oscillating function, and that averages out to 0. So we're left with p times epsilon s prime minus epsilon s times delta k1 k2. So if we go back to the first term, or the second term in our expansion, where we have one interaction, then we see that this is equal to delta k1 k2 p times epsilon s prime minus epsilon s, and then we have the propagator g0 at crystal momentum k2 omega squared, because these are now propagators with the same crystal momentum. So that leaves us with one more term that we want to discuss. In terms of physics, though, it is nice to realize that whereas a single impurity or a single specific random realization locally, of course, does not conserve crystal momentum, because we average over so many different random distributions, in the end only the Green's function where the crystal momentum is conserved is going to contribute. So we still have a delta k k1. Now let's have a look at the case where we have two scatterings, two interactions with the impurities. And for this we have to separate two different cases. So in terms of our expansion, we look at this case where we have two interactions and three propagators. We can either scatter twice at the same site. Or we can scatter at site J and site J prime, which is not equal to J. Now, why do we distinguish these two cases? Well, what is the chance to have an impurity on site J? That is chance P. And now, when I have an impurity at site J for my first scattering event, I will definitely have an impurity on site J for my second scattering event at site J. So the chance to have an impurity when I want to scatter two times at the same site is P. Now we can scatter at site J and at site J prime. And in this case, to be able to do this, we need to have an impurity at site J as well as at site J prime. So the chance to have an impurity at site J and J prime is equal to P squared. So a chance P squared to have an impurity on both sides, a chance P to have an impurity on site J. So in order to calculate this, we have to make the distinction between these two cases. If we look at the average of our Green's function for two scattering events, we have our sum G0, K1, K1, omega, which does not depend on the random distribution, so that we can take outside. Then we have H1, K1, K3. Here we have to take the average. G0 again, now propagating with crystal momentum 3. H1, scattering from K3 to K2. And then the bare propagator scattering or propagating with crystal momentum 2. Our bare propagators are propagators in a system without impurities, so they do not depend on the impurity distribution, and we can nicely take that outside of the average, such that we have the sum over all crystal momenta K3, and then the average over H1, where you go from K1 to K3, times H1 going from K3 to K2, and then G0, K1, G0, K2, and G0, K3. Now let's just have a look at the average over all random distributions of the product of H1, the matrix element where you scatter from K3 to K1, or where you scatter from K2 to K3. And this is given as the average over sum J and J prime, our random distributions at J and J prime, 1 over V squared, epsilon S prime minus epsilon S squared. I'm just putting in the definitions of H1 as we had before. And then we have e to the minus I, K1 minus K3 dot Rj times e to the minus I, K3 minus K2 dot Rj prime. And again, I don't have to add the creation and annihilation operators because my Hamiltonian creates and annihilates at k prime and k, but I'm looking at the matrix elements where k prime is equal to k1 and k is equal to k3, or k prime is equal to k3 and k is equal to k2. And it now becomes important to distinguish the two different cases. So let's have a look at the case where j is equal to j prime. And in this case our average over the product of the Hamiltonians is equal to p. We can again change the order in which we sum over all lattice sites and average over all random distributions, and then realize that gj is now equal to gj, which is just 1 times 1, and therefore becomes p and not p squared. And then we have these sums over j and j prime, which is now a sum over j, and that each one of the Fourier transforms as a delta function, so that we have delta k1 k2 epsilon s prime minus epsilon s squared. And the other one is gone because we have e to the minus I minus k3, so that's e to the I plus I k3 times rj. And here we have e to the minus I k3 rj, and j is equal to j prime. So also that will disappear. So with that we can of course go back to the original problem, which we have here, which is equal to delta k1 k2 g0 k2 k2 omega, and k1 is equal to k2, so we have this one twice. And then we still have p epsilon s prime minus epsilon s squared, and we have a sum over k3 1 over v g0 k3 omega. I can travel from side j to side j because I'm scattering at the same side with any crystal momentum that I have. Well, this is nothing more than the Green's function in real space, so this is delta k1 k2 g0 k2 omega squared p epsilon s prime minus epsilon s squared g0 r omega. And it doesn't depend on which lattice side you calculate the local Green's function, because we are in a periodic system, so all sides are equivalent, and this is just the densities of states, or better said, the imaginary part of this Green's function is the densities of states. Now we can also look at the case where j is not equal to j prime, and again we have to look at the average over the product of two impurity Hamiltonians, or Hamiltonians that describe the interaction with the impurity. And what we have is very similar, just that now the average over the two random distributions doesn't become p but becomes p squared, because you now are looking at the probability to have an impurity both at side j and j prime. And then we have a delta k1 k3, because you have a sum here over all lattice sides. We have a delta between k3 and k2, because we have here a sum over all lattice sides. And before you had only one sum over the lattice sides, and r was equal to rj, thereby annihilating the k3. Now we get two delta functions. And we have an epsilon s prime minus epsilon s square, such that the Green's function with two interactions becomes, we now have k1 has to be equal to k3, k3 has to be equal to k2, so all of them are equal to k2, delta k1, k2, g0, k2, k2 omega cubed p square epsilon s prime minus epsilon s squared. So we have seen that we can do all three levels of interaction with either 0, 1 or 2 scattering events. And with that, the Green's function scattering from k2 to k2, k2 to k1, averaged over all lattice sites, or averaged over, over all random distributions, is equal to k1, k2, g0, k2, k2 omega. So either the propagator where you don't scatter at all, or the propagator where you scatter once, which then has a contribution that is proportional to the on-site potential times the probability that you have an impurity g0 k2 k2 omega squared plus, and now the probability to scatter two times k1 k2, and this we have to distinguish between events where you scatter two times at the same lattice site, p g0 k2 k2 omega square r omega or you can scatter at two different lattice sites, epsilon s prime minus epsilon s squared p squared g0 k2 k2 omega cubed. You propagate to that lattice site, you scatter, you propagate to some other lattice site, you scatter and you propagate again. So we have three propagators in k-space here, whereas here you have to have the coherent superposition of all these scattering in k-space such that you go from the site to the site where you started, which is g0rr of omega. And then of course we have the higher order scattering events, which we now have to generalize from what we have seen here. And there's first of all a very important observation that we make, and that is all our Green's functions include a delta k1 and k2. So once we have a very large system, then if you start with a particle with wave vector k, you will be able to find it at some point later time in that same state with wave vector k, but the probability to find it in any other state is going to be 0 because, well, of course it can scatter. We'll find that some of these states decay, they move to another k vector. But as there are infinitely many states and you only have a finite weight going in there, the weight of each of these momenta is going to be 0. So we will find that our Green's function is diagonal in k-space and not conserving the momenta unless you integrate all these zeros, the infinitesimals of the other k vectors. So in order to continue, we will use diagrams to extend this to infinite order, just to make sure that our notation is a bit shorter and easier to handle. And the only thing that these diagrams do is basically replace recurrent parts in our expansion that we have seen all over the place. So one of the things that can happen is that you propagate with a certain crystal momentum and you scatter from an impurity. If this happens and you scatter once, then we have a vector that is adding, that is epsilon s prime minus epsilon s times p. And for that we have to make sure that you scatter once at a different site than before. If you would scatter at the same site, then I for sure know that you have an impurity there, so we don't have to add another p. Now we can come, we scatter at one site, and then scatter at that site again, and again, and again, and again. And we can do that one time, or two times, or three times, or infinite times. Scatter once, to infinite many times. On the same site. This has the prefactor in our equations of P. You have to have an impurity, otherwise you can't scatter, but we do not have to take this for each time we scatter, because when I know that my site has an impurity, it has an impurity. Then we have the probability to scatter, which scales with the potential that we have, times the Green's function to propagate from our site R to our site R, n minus 1. If I scatter once, I don't have to propagate back. If I scatter twice, I have to propagate back to the site where I started before. This is a geometrical series. Of course, we have to worry about convergence ranges, but we know these are analytical functions. The poles are well localized, so we can always do analytical continuation. And we have 1 p times epsilon s prime minus epsilon s more than the Green's functions over 1 epsilon s prime minus epsilon s G0 R omega. So that's the contribution that we get from scattering once to infinitely many times on the same site. Well, then we have our bare propagator. That is the propagator that we have for an electron propagating in a crystal without impurities, which is given as 1 plus I0 plus minus the energy momentum dispersion, and we have our full propagator, which will indicate by a double line going from K2 to K, which is G K2 to K1, which is the object that we want to calculate. So our full propagator is given by the bare propagator, where we do not scatter, plus the propagator, where we do not scatter, going from K to K. Then we scatter once to infinitely many times on the same site, and again propagate with crystal momentum k, or we can propagate with crystal momentum k, scatter 1 to infinitely many times on the same side, propagate with crystal momentum k, and can scatter 1 to infinitely many times on the same side, etc., etc. And this is nothing else as the sum of n is 0 to infinite of the bare propagator times scattering 1 to infinitely many times on the same side times the bare propagator to the power n. We can now insert back our equations to see that our full propagator is given by G0 k omega times the sum, I can take this one outside of the sum, n is 0 to infinite of scattering 1 to infinitely many times on the same side times the bare propagator. And we can do this 0 to infinitely many times. This again is a geometrical series. So what we have is G0 k omega times 1 over 1 minus p epsilon s prime minus epsilon s G0 k omega divided by 1 minus epsilon s prime minus epsilon s G0 RR omega. Beautiful. We have our Green's function. So now we should Fourier transform and see what the lifetime is in which your state created with crystal momentum k stays with crystal momentum k. Now, before we do that, we can make a few simplifications and introduce the self-energy. And we can first of all multiply this with G0 k omega minus 1, both top and the bottom, such that we get that this is 1 divided by G0 k omega minus 1 minus p epsilon s prime minus epsilon s divided by 1 minus epsilon s prime minus epsilon s G0 RR omega. Now the inverse of your Green's function is just omega minus epsilon k. So what we have here is 1 over omega plus I0 plus minus epsilon k0, which is the inverse of your Green's function. And then we have our correction to that, and that correction we will call the self-energy. With the self-energy, sigma of omega is equal to p epsilon s prime minus epsilon s divided by 1 minus epsilon s prime minus epsilon s G0 R omega. We now can Fourier transform from frequency space to the time domain, and for that we can make an approximation, and that is our Green's function becomes large when omega is roughly equal to epsilon k, So instead of taking here the self-energy as a function of omega, we can take the self-energy at epsilon k, because that is the leading contribution. And then this, in principle, complex function becomes a Lorentzian again, such that our Green's function in the time domain then is roughly given by delta t times the complex I e to the minus I epsilon k plus the self-energy of epsilon k times t. And now you can see that the imaginary part, or better said, minus the imaginary part of the self-energy is equal to 1 over tau, your scattering time. And of course, we also have a real part of the self-energy. And the real part of the self-energy adds here to the energy momentum dispersion, so that is a shift of the poles. If the self-energy is a constant, then you should be able to have just an imaginary part, and the real part can be 0, so the real part can be completely absorbed in the definition of H0. Now, of course, the self-energy cannot be a fully imaginary constant, because it tells you how your system couples to the rest, or in this sense, couples to the impurities. And of course, for very high frequency, you're not allowed to have a response, because your particles have a mass, you can't be infinitely fast. So the imaginary part of the self-energy has to die off to 0 for high frequencies. So you always have to have some real part and some shift of poles whenever you start to include a self-energy and an imaginary part. So any particle that has a decay has a shift in energy that corresponds to that. Now, the definition of a self-energy that we have here is in principle fully in line with definitions you might see in quantum field theory or in particle physics, but now used in the context of condensed matter theory, and even in the use of a reasonable simple example where we have no full many-body interactions, but only one particle interactions, such that we can actually solve and do a lot with these kind of systems. We normally talk about particles when the self-energy is 0, when they have infinite lifetime. What we see here is that particles decay, and at that point I would normally talk about quasi-particles. So for a particle, we have sigma of omega goes to 0, tau goes to infinite, and quasi-particles I would say that the imaginary part of the self-energy is no longer equal to 0, such that their lifetime is finite. In particle physics, this is also known as a resonance. If you look at Wikipedia, you might find slightly different definitions. I don't think that the current definition of Wikipedia is fully self-consistent. But it's not so different either. I do not say here what the reason is that your self-energy is non-zero. I would say as long as you find a non-zero self-energy, independent of it's a one particle or a two particle or a three particle interaction, you start to get quasi-particles that move through an effective potential. And that's exactly what we see here. So I hope I've given you a nice overview, and with the use of an example, how one can obtain a self-energy which then gives you a finite lifetime. We have seen before that in principle this form for a Green's function can be very generally obtained. When you think about continuous fractions, you have some Hilbert space or some part of your Hamiltonian in which your particle live, which we can diagonalize such that we have eigenstates there with infinite lifetime, and a state created in an eigenstate will stay in that eigenstate. The only thing that happens when you do time evolution is that you get an additional phase, such that the Green's function is equal to, well, maybe a phase oscillation, but then a constant equal to 1. Now when you have this system and you couple it to additional states or additional interactions, you get a self-energy. You do have to require that you couple it to an infinite set of states, otherwise this would be just a discrete set of poles without an imaginary part in between. But if you now couple it to an infinite set of states, you'll get self-energy in there, and at that point your particles start to decay. So a particle that propagates in a formally eigenstate of the bare Hamiltonian are no longer eigenstates, but they decay. And the decay is given by how your local system couples to the rest. How the subpart Hilbert space A couples to Hilbert space B. As we did for the continued fractions. And that of course is a completely general topic that you can always do. And we've even seen with the introduction of Lanczos algorithms how you completely general can always generate such kind of continued fractions representations of your Hilbert space. And if you do this now with blocks instead of single states, you can get, well, particles moving, still having reasonable complex dynamics, and then a self-energy that describes how we decay into the continuum. I thank you very much for now. We see each other later. Stay healthy.